Welcome to Unit 1, Lesson 1. It says, if you can't measure it, you can't improve it. The only place that work comes before success is in the dictionary. Or success comes before work, excuse me. It says, students should be able to measure mass, volume, length, and time with accuracy and precision. You should be able to identify the number of significant digits in a measurement and the purpose of significant digits, and you should be able to convert between common metric units. So, what you already know. Well, you don't know much. You know this could be chemistry, this could be physics, you might be an IPC, but this is your introduction to this. And that chemistry is generally called the central science, whereas physics is generally considered to be a little bit more mathematical, although it has physics concepts in it, and that and chemistry are both very different from biology. So, what you should have learned in the lab. You should have learned that there are multiple tools capable of holding liquid, and that certain tools are better for measuring volume, and that you have beakers and flasks for mixing, burettes, graduated cylinders, and pipettes for measuring. So, the fundamental units of measure, there's really only 7 things that we can directly measure. And those 7 things are length, which is measured in meters, mass, which is measured in kilograms, temperature, which is measured in Kelvin, number of moles, or number, which is measured in moles, current, which is measured in amperes, time, which is measured in seconds, and luminous intensity, which is measured in candelas. So you should be familiar with a lot of these already, like electric current, temperature, time, length, mass. You may not be familiar with moles or luminous intensity, which is another word for brightness, but let's look at all of them right now. So length is any quantity with distance dimensions. So almost all length tools are analytical in the sense that you actually have to read them directly. So if I wanted to look and see how long something is, I have to look at it and then I have to figure out how long it is. There's no digital readout. So if you were to look at this one, see how it starts at 25 but it's not at 26. So I know it's 25. And then it goes over 1, 2, 3, 4 marks. And it's not quite to the fifth mark, so it's zero point 0.4. And then I have to estimate that last digit because there's nothing to say it's 0.4, 1, 2, 3, 4, 5, 6, 7, 8. So you have to estimate it. And to me, it's a little bit further than the 5 mark, so I would say that it's 25.48. With all analytical tools, you have to estimate that last digit in order for it to be as accurate as it can be. All right. Mass is resistance to change in motion. It's measured in kilograms, although in chemistry it's more commonly measured in grams because we tend to not deal with large mass values. But in physics, it's definitely large mass values, so it tends to be in kilograms. Kilograms is the standard unit. Mass is measured with a balance. Now, that balance can either be a digital balance like this, in which you just read the balance exactly as it says, or it can be an analytical balance, which is something like you see here, a triple beam balance, in which you have to estimate that last digit. So with a triple beam balance, you would read the first mark, which is 300. You would read the second mark, which is 30. You would read the next mark, which is 5. And then you look at this and it says, it's not 5.0, so you say 335.00 grams because it's exactly on that mark. And I could exactly read zero point 0.1 because of these lines right here in between. So I have to do this as my estimated digit. You always have to do that with analytical tools. Time is the interval between events measured in seconds. You, of course, read the exact reading on a digital tool, and then you can estimate with an analytical tool based on where you stop it. Now, we tend to not see these anymore. You don't see these analytical stopwatches. They're nowhere near as accurate unless it's something like a Rolex, which has a continual motion. Most watches will click between 1 second to the next. There's no continuous movement throughout them. Okay, a luminous intensity is a measure of the power emitted by a light source, so how bright it is. Generally, this is a digital tool. You don't tend to see analytical luminous intensity tools, so generally you just have to read the reading that's right there. In chemistry and sometimes in physics, depending on what you're looking at, we often refer to the luminous intensity as a fraction or percentage that we actually call the absorbance. That's more common in chemistry than it is in physics. Temperature is an objective measure of how hot or cold something is, referring to the average kinetic energy of a sample. So a sample is going to have kinetic energy. Something that's hot has a lot of kinetic energy. Something that's cold has a little bit of kinetic energy. Temperature is a measure of that. There's lots of different scales for temperature, including the Fahrenheit, which we will not use, the Celsius scale, which is much more common in this class, and the Kelvin scale, which is actually correct. The Kelvin scale is actually the most correct example that you have, but we will use Celsius and Kelvin interchangeably. Now, when you have a digital tool, you just read it. When you have an analytical tool, you would have to estimate one digit more. So to me, this right here, I can read it to 80, and to me, it's not quite to 85. So what I would say is this is 84 degrees, and that's me estimating one digit in between the marks of 80 and 85. I'm estimating in between there. Number of particles. The number of substance is measured in moles. So we tend to think of 1, 2, 3, 4, 5 like the number of things that actually happen. But when we start to get into things like atoms or electrons or something like that, you really deal with such a large number that you have to refer to it as a mole. Just like 1 dozen refers to 12, 1 mole refers to 6 times 10 to the 23rd of that substance. So if you had a mole of donuts, you'd have 6 times 10 to the 23rd donuts. If you had a mole of people, you'd have 6 times 20 to 10 to the 23rd people. So that's the number that we tend to see. Electric current is something that we'll cover exclusively or mostly in physics, but current is the measure of charge that flows past a certain point in a certain time. It's measured in amperes. You will see both digital and analytical ammeters, which is the tool used to measure electric current. Once again, if it's digital, you just read it. If it's analytical, like you see right here, you really have to estimate that last digit. Okay. Um, what should you record in your lab notebook for the values below? Be sure to indicate what the measurement is for. So this right here, I will record 31.4 degrees Celsius, and that is a temperature. This right here is 14.273 meters, and that's a laser, it's a digital measurement tool, length measurement tool. So I would record 14.273, and I would record 100.0 for this ammeter reading. So those are digital tools that you read exactly. These ammeter tool or these analytical tools are going to be a little bit different. So if you were to measure the length of this bolt, you would actually have to say 6.4, because to me that's not quite to the 5, 6.4 and then 8 millimeters. You would also have to say on this one, we're going to measure it on the Celsius scale, which is this one right here. You'd have to say this is 30, 32, 34, 36, 38, 40. So to me, this is between 32 and 34, which means I'm going to have to estimate between those, and I'm going to estimate it to be 33 degrees Celsius. It says, why can you not directly measure the speed of a car? You cannot directly measure the speed of a car because the speed is not one of those fundamental units of measure. Instead, you can measure the distance or the length, you can measure the time, and you can divide the two together, but you're combining two measurements. So you cannot directly measure it. Significant figures are the degree of accuracy to which you are measuring an object, and it's really, really important in lab and lab analysis. Now, it's going to be less important depending on your teacher's way of looking at it whenever you're doing calculations. But every time you do a lab, you should be using significant figures to indicate the degree to which you measured something. It's really that important. So it is important that you record the correct number of significant digits and that you be able to identify the correct number of significant figures. So the rules are 1 to 9 are always significant. Placeholder zeros are not significant, and what I mean by a placeholder zero is if you were to say 50, this right here is a placeholder digit. I could easily write that number as 5 times 10 to the second, and I didn't use that second zero. So because of that, that's not a significant zero. Likewise, if I were to say 0.0001, I could easily write that number as 1 times 10 to the minus fourth, and I didn't use any of these zeros. So they're not significant. However, once you put that decimal down, this is saying everything in front of it is now significant. These are all significant at this point. Okay, so whenever you have that decimal, it's really important that you are aware of that. Likewise, if you were to have 50.0, there's really no reason for you to put those there unless you measure to that specific amount. So you're going to take some practice. You're going to try and figure out if zeros are significant or not. Zeros are really the tricky part with significant figures. So let's look at this. It says, how many significant figures are there in the number this? Okay, so if I were to look, I could write this number as 1.016400 times 10 to the minus second. And some of you may be saying, but wait a second, you don't have to write those two zeros. You're right, I don't have to, but there's no reason for them to be here unless I were specifically saying that I measured out that far. In other words, if I would have written the number 0.010164 and stopped it, that means something. I didn't have to have those. So because of those, these zeros right here are significant. These two zeros right here are not. And any number that's in between two significant numbers, any zero that's in between, also has to be significant. I have to use that number. So because of that, I have these all as my significant figures. So I have 1, 2, 3, 4, 5, 6, 7, 7 significant figures. This one says, is it fair to make someone valedictorian when one person averages a 103.654, the other one a 103.658? And, you can go back and forth on this. Answers may vary, but really the answer is no, because we stopped cutting off grades at 99 and 100. I didn't give you a 99.364, so it's really not fair to compare to that decimal place whenever you're looking at the overall averages. You can stay only within the value of that was measured. So you should be able to measure something at 100 or 99, but these two averages are essentially the same according to scientific purposes. There is a difference between a derived unit and a base unit. And a derived unit in this case is whenever you combine those 7 fundamental units of measurement in order to get a new unit. And one of the most common is density. Density is a measurement of mass and also volume. Well, volume itself is a derived unit. Volume is length times width times height, and you have a three-dimensional structure. Whenever you have that three-dimensional structure, that's a derived unit of 3 dimensions of length. So you have volume itself, which is derived, and density, which is taking mass and dividing it by another derived unit. So you have these derived units that are combinations of the 7 fundamental units of measure. Base units are the main term of the measurement: liters, meters, seconds, amperes, grams, molarity, millality, joules, lots of them. But you can put a prefix in front of them, like we've already seen with grams. Grams generally refers to the kilograms as well. The prefix units change the value of the measurement from 1 meter to 1 millimeter squared. Um, so 1 millimeter is not the same thing as 1 meter, which is not the same thing as 1 meter squared. So you really do need to be real careful about using your prefix values. Okay, so the metric values, you need to memorize these. You need to know what tera, giga, mega, kilo, centi. It needs to be one of those things that just comes to you, not something that you have to look up, and how to convert between them. A lot of times it's helpful for people to think about it in terms of hard drive space for a computer, like a terabyte versus a gigabyte versus a kilobyte. Um, but it's one of those things that you just have to know. Dimensional analysis is an organizational tool that is required in chemistry and in physics for conversion factors. You must be able to do this. It's based on conversion factors, which are a equal form of 1. So let's go ahead and do an example here. You have 9,500 terameters, and in 1 terameter, if you look at that chart that you were supposed to remember, is 1 times 10 to the 12th meters. Whenever you multiply this out, you get 9.5 times 10 to the 15th meters. Okay, how could you measure the speed of a car? You could measure the distance, and you could divide it by the time, like we talked about earlier. Okay, using dimensional analysis, show how many hydrogen atoms would fit in a 1.6 kilometer line. So you have 1.6 kilometers, and you would say that 1 kilometer is 1,000 meters. And you would say that 1 meter is 1 times 10 to the 9th nanometers. And then you would say that 1 nanometer is 10 hydrogen atoms. These things are all equal to each other. They're conversion factors. So because of that, you take this, you multiply it all out, and you get something along the lines of 1.6 times 10 to the 13th hydrogen atoms. And finally, this is the density of water is 0.997 grams per mil. What should the units for density be if it was in standard units? So grams has to be in kilograms. The standard unit for grams or for mass is kilograms. So I'm going to have to convert grams to kilograms, and I'm going to have to convert milliliters to liters to be a standard unit. So I'd say there are 1,000 milliliters in 1 liter, and then I would say that there's 1,000 grams in 1 kilogram. And if you look, kilograms is going to stay, grams is going to cancel with grams, milliliters with milliliters, 1,000 is going to cancel with 1,000, and you get the exact same number, but now in kilograms per liter.